I'm Heel.
I'm Bill.
And I'm Please.
And together, we're Hillbillies. We're getting ready for our Daytona 500 race for these drones here. So we're gonna head on over to the park. Because we ain't fast enough. We gotta get faster. We're gonna interview some people about some PIDS. Let's go, fellas.
Out here and I can take you for a ride on my big green tractor. We can go slow or make it go faster, down through the woods and out to the pasture. Long as I'm with you, it really don't matter. Climb up in my lap and drive if you want to. Girl, you know you got me to hold on to.
What do you think about PIDS?
PIDs are very important. If you don't know how to tune your PID, you won't be able to fly your quad.
You heard him? Oh, you're wait. Hold my cigar. We're gonna go over what PID stands for. So, P for proportional is how much the drone jerks. We got I for integral, how long it takes for the drone to do the jerk motion. Then we got D for derivative, and that's how smoothly it ends the jerk.
Oh, hey, hold my cigar. So, PIDS, as Brandon said, the P is the jolt, the D is how smoothly it ends the jolt, and the I is how long it takes basically the whole motion to happen. Basically, the whole thing based around PIDS is based around how much stick you have to get for a certain move to occur. So, let's say you're at 0 stick on the white stick and you want to do a flip. You'd go like a front flip, you'd push all the way, and then you'd let it flip, and then you'd stop and pull back. Your starting point is at 0, and the desired point is at the top, because that's your max rotation. So if you look at a graph and you have your stick at 0%, and it's not moving because it's just staying there at 0. And let's say the max has the drone spinning at 600 degrees a second, which is pretty average. Basically, when you start giving it stick, your graph line is going to start moving up. So you have your starting point and you have your destination. Basically what the P is saying is how sharp it's going to go from 0 degrees up to your desired destination. But because of the P and because you have momentum on the quad and it's still flipping, you still have to, it's going to overshoot your destination a little. And because of that, with a P, you get like a sine wave. Now, if you have your P tuned really high, this overshoot's going to be a lot. But if you have your P tuned pretty well, the amount of overshoot you have can be minimized, and then the other PIDs will help smooth that out. Now we're going to talk about the D tone, which is after the P, it's how it smooths it out at the endpoints. Because if you have a really low D, it means that this thing's going to do like a sharp maneuver, and then at the end it's going to get a little bit of oscillation, which you don't want because it cuts down on speed and everything. It causes your props to flex, and you don't want that. So if you have a low D, it makes it so, or perfectly tuned D, it makes it so that endpoint is smooth, and so you could go from like one flip to like a wall or whatever you want, making it all smooth. Now that's all with like a stick again. So if you start at 0% and then you go up to like a wall 600 degrees a second, basically your P, because all these PIDs are happening at once, your P is having it go uphill, trying to get to your desired point. What your D is doing, your D happens once you get close to that desired point. The D is telling your P that you're getting close to the desired point, and it's gonna start giving a downward force onto it so it doesn't overshoot it and have to correct more. So with a good, properly tuned D, the sine wave that your P makes should be minimal, because at each interval it's telling it to pull down or push up to reach this desired point. Now we're going to talk about one of the least important part of PI and D, and that's the I. It doesn't get much love because not a lot of people think about it as much, but I think it's pretty important, and us hillbillies need it to go fast. So basically, you know, when you're giving it stick to, let's say, do a split S, which is basically where you do a barrel roll, but instead of completing it, you do like a half backflip. So you go halfway through a bell wall and then pull back to do. So it's used to change directions. But when you give it stick, you know, your P is getting up to your desired point, and your D is telling it to go down because it's getting close to your destination. Basically, what the I does over a long period of time is it tells your P that you're getting really, really close, and it tries to extend the time it takes to get to that destination so you don't overshoot it, because overshooting it creates L. So your I helps you get as close to your desired point as possible without going over, and it makes it so your D doesn't have to do as much correcting of the P.
Howdy. We're gonna go over what a loop time is. A loop time is going through one PID cycle. And on average, one PID cycle is 1 second. And high loop time and good PIDs mean smooth sailing. Howdy, partner. Howdy.
We can go to the show, we can stay right here, and I can take you for a ride on my big green tractor. We can go slow or make it go faster, down through the woods and out to the pasture. Long as I'm with you, it really don't.
Now after watching that video, you can see how shaky it was. So what we're gonna do is we're gonna try to change some of the PIDs. So what we do is we plug it into the programming software, and this software will allow us to change the PIDs. And basically right now it's on default. Once we go in here, you can see that it's really jerking the tones and stuff. So what we're gonna do is we're probably gonna end up raising the P. The P for the wall, the pitch. The yaw was pretty good, so that we're not gonna touch yet. And then the D we're gonna raise for him too to smooth it out a little. And then we're gonna go fly it again and see how much of a difference that makes.
Wanna do, baby, I don't care. We can go to the show, we can stay right here, and I can take you for a ride on my big green tractor. We can go slow or make it go faster, down through the woods and out to the pasture. Long as I'm with you, it really don't matter. Climb up in my lap and drive if you want to. Girl, you know you got me to hold on to. We can go to town, but baby, if you'd rather.
So now that we're back, you can see that we had to come back and change the PIDs, and you can see how just making this small difference and just raising the values by a little and lowering a couple other ones made a huge difference in how smooth the quad flied. Basically, we had to fly it and land it and change these values about 5 times until we figured it out. So that was kind of.
Continuation is when you increase the throttle, the rate of the PIDs increases to reduce oscillations. So right here we have PIDs, P, I, and D. P is expressed like this. I is expressed like this. And then D is expressed like this. Okay, so P is proportional to standard error. It is a large. So basically, if standard error is a large positive number, P will be proportional to that and also be a large positive number, accounting for gain factor, which is K. This is the gain factor right here. So using proportional control to basically compensate for error. So basically, say we have a set value of 200 RPM for the motor of our drone, but the actual process value is, let's say, 250 RPM. It's not what we set it to. We basically would use PIDs to try to correct that error to get it closer to get the actual value closer to the set value. So that's what the whole point of PIDs are. So, and then I, which is another part of PIDs, has its own growth factor, and it takes the derivative of the standard error over time. This basically it's basically doing based on the past standard error, it's going to try to eliminate it. The standard error that's happened before. So it seeks to eliminate the error by adding a control factor from historic cumulative value of error. So it basically stores up all the mistakes it's made and then tries to correct the error based off of that. So that way the actual value is closer to the set value. And then D, which is another part of PIDS, is an estimate of future trend of the error. So based on the standard error's current rate of change, it seeks to reduce the effect of error by exerting a control influence generated by the derivative of the error. So it basically tries to predict how the error is going to change based on where it's at currently, and it applies a force to make that closer to the actual value to eliminate the error. So then when we combine all of these together, all the factors of PIDS, we get this equation, which is U of t is equal to growth factor of the standard error plus growth factor of the integral of standard error over time plus the derivative factor times the derivative of standard error over time. So basically this equation allows us to get closer to the set value based on where the actual value is currently at, right here, based on past records, basically what's happened before, and based on what it predicts will happen. So when we combine PIDS, we get a value of UT, which is closer to the set value than the actual value would have been with that error. So because we're eliminating this error, or we're doing our best, we're proportionally responding to error to eliminate it, we are getting as close to the set value as possible thanks to PIDS.